Welcome. We want to take a look at an example of identifying asymptotes and locations of holes, and we want to plot those once we have them. All right. Our function in this case is a quartic divided by a cubic, so degree 4 divided by degree 3. So as far as a horizontal asymptote goes, there isn't one. Again, when the degree of the numerator is less, we will have a horizontal asymptote of y equals 0. When they are the same, the degree of the numerator and denominator, we'll have a horizontal asymptote of the ratio of leading coefficients. And when the degree of the numerator is higher, there is no horizontal asymptote. There is, however, a slant asymptote in this case when the degree of the numerator is precisely 1 degree higher than that of the denominator. What we can do is we can perform the polynomial division to find that f of x is equal to 2x plus 1 plus 7 divided by x minus 4. Now, it would be expected that you would show the work if you were to complete this for an exam or a homework problem, that sort of thing. In this case, I'm just sharing what we should find. I would encourage you to practice that polynomial division to find this. So what we have is we have a slant asymptote of y equals 2x plus 1. Okay, this portion of that gives us our slant asymptote. For vertical asymptotes, we'll go ahead and simplify so that way we can observe which factors are remaining after simplification in the denominator. Cancellation of x minus 5, cancellation of x plus 1, and the only factor that remains is x minus 4. So we get a vertical asymptote at x equals 4. Now we can talk about the holes in the graph. Holes occur when we completely remove factors from the denominator. So since these are completely eliminated, I can't have x equal to -1, and I can't have x equal to 5. I just need to find out the function values. Excuse me. I suppose it's not really the function values because we won't have x equals these things. All right, for x being -1, if the function were defined, what would it be? Well, it would be what I can plug in here after simplification. So y would be equal to -1 minus 3 times 2 times -1 minus 1 divided by -1 minus 4. -1 minus 3 is a -4. -2 minus 1 is a -3. -4 times a -3 is going to be a -12. And -1 minus 4 is 5. -5, that is, we have a cancellation, so we have 12/5. There is a hole at -1, 12/5. All right. There's also a hole when x is equal to 5, or where x is equal to 5, and that hole is given by 5 minus 3 times 2 times 5 minus 1 divided by 5 minus 4. 5 minus 4 is just 1, so I only have to consider the numerator. 5 minus 3 is 2. 2 times 5 is 10. 10 minus 1 is 9. So I have 2 times 9, which is 18. So there is a hole at 5, 18. Now this is a pretty high value here. So what I'm going to do is I'm going to go ahead and adjust our scaling essentially. I'll still use 1, 2, 3, 4, 5, right? Use the same scale there. But to get the 18 on here, what I'm going to do is I'm going to have 4, 8, 12, 16, 20. So my 18 will be in there now. That looks good. So I want to plot each of these things. Let's start with the horizontal asymptotes. There are none. Slant asymptote of 2x plus 1. So a slant asymptote of 2x plus 1, I'll have it crossing right here. And then I'm going to, for every 1 that I move over, I will move up by 2. So it's going to move up by 2 to right here, up by 2 to right here, up by 2 to right here, up by 2 to here, and up by 2 to here. So it doesn't look very steep because of the scaling that we have done. Oh, not there, but here. There we go. Here, 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 and here. That looks pretty good. Lots of dots for me to connect. We don't have to have all of those. Of course, we only need 2 points to determine the line. I'm not using a straight edge. I'm just trying to trace here. So, oh, and you know what? That needed to be dashed. So I'm going to go ahead and erase a couple of points just to get us something that's a bit more dashed. There we go. Dashed line. Now I would like to plot the vertical asymptotes. There's only one, x equal to 4. So this is actually 4 over here. So x equals 4 gives us our vertical asymptote. And then we have a hole at 2 holes. So -1, 12 fifths. -1 and positive 12 fifths. Yes. -1. Positive 12 fifths, so a little over 2. That looks good. And then we have another hole at 5/18. Oh, and it looks like I made a mistake here. You probably caught it already. 18 should be right here. This looks good. 5/18. But when I looked at these, I said to myself, which you'll find when we start graphing these rational functions, I found that I have something in this corner here, right? I've split the plane into 4 pieces with these asymptotes. And I found something up here and I found something here. And I didn't like that. If I have something up here, the other piece should actually be down here. So I'm guessing that I missed a negative. And of course, I said a -4 times a -3 gives me a -12, and that was an incorrect statement. So we can correct ourselves there, right? It's not about not making mistakes. It's about fixing the mistakes and recognizing them when we make them. Okay, so making mistakes, it happens. The question is simply, can we observe that we did and fix it? In this case, yes, excellent. So this should actually be a -12 fifths. So we'll plot that appropriately closer to here, a little bit further than halfway down one of these, right? This is going to be a -2 right here. This is a -4. So between -2 and -3. Excellent. I'll point out that this is -1, -12 fifths. This was y equals 2x plus 1. And this was x equals 4. I've labeled everything so that way the communication is clear as to what each of these pieces is.